Okay, so today the topic that we are going to cover, that is mainly related to the pre-processing and post-processing too. Okay, actually this week turbulence model is scheduled, but one of our mentor has is a pre-scene scheduled in this week, so that is why that session we have postponed into the means next week, and this week we are going to cover the means every option and the thermophysical model. Okay, and I am also going to cover how you can automate your post processing using the ParaView. So I think you means some of you might heard that you can also write a Python coding in ParaView. Okay, so in if you know that access that quality of how you can access the ParaView Python scripting, then you can optimize your processing tool. Sometimes it happens that you want to do post processing. In that scenario, if you have some idea about how you can use write the Python code in ParaView, and then you can means repetitive task you can do using the that script only, and it's not much difficult. You don't need to know means you don't need to have a means idea about the Python coding. So you just whatever the steps that I am going to show you, if you follow those steps, then you can easily write those codes, and you can do whatever the repetitive task you perform using the GUI based ParaView software, that you can perform using that scripts. So that those things that we are going to see, we are also going to see some every function objects, and also we are going to see how some of the pre-processing tools, and there are other things that whatever the post-processing tools or pre-processing tool are there that we are going to cover today. And since there is lots of utility in OpenFOAM, speaking about the pre-processing and post-processing, so there are lots of means codes are already written in OpenFOAM. So some of the things I'm going to cover today, and if you know that how that's why I did not make any folder today. Okay, so just I want to show you that. Let me go to the run folder. Okay, so maybe we can create one folder for this week. So if you means I just want to show you that how you can have access, that how you can know about any type of utility open available in the OpenFOAM. So if you means if you have idea that how you can access means basic concept behind these things, then you can have better idea about how you can means this. There are many types of utility. Let me show you, then you have better idea. Okay. So I will also request everyone to just this, since this is a hands-on practice. So just whatever things I am typing on the terminal, or whatever things are I am performing during this live session, you should also try to do from your side. So we can create week 06, and so if maybe I'm fast, then you can just let me know in the chat box, but just try to do whatever I think I'm going to perform. So this is the folder that I've created. Okay, so first let me show you that OpenFOAM. So this is the OpenFOAM 6 installation is here. So there are different application folder, bin folder, doc folder, and etc folders are available. If you know that I said that there are these three folders are very important for us, because there is application is already installed in solver test, that if you want to know about what are the different means for example this different C++ classes are given, that you can have better idea here. And maybe some of the things we can means we are going to cover also some of the examples from the test. Okay, like I wanted to cover this code stream. So if I get the time in the last, then I will show you that how you can use the code stream for means developing a boundary condition. Okay, and this is the where this post processing, pre-processing, or parallel processing utilities are given here. Okay, so if you go into the pre-processing, okay, so there are different things like change dictionary, engine swirl, home set, CST, map fields, and like this set fields utility that we are going to use today. Okay, so this is a generally basic code is written here. Okay, if you open this, let me close first everything. So in set field, this is the codes written here. So we don't need to worry about the coding. Okay, we are just going to that how you can use this utility, that is the set field. Okay, so this is this utilities folder that you are seeing here. Everything you can see are that different codes is available here in this folder. If you go to the application folder, and if you go to these things, that you can see that there are different codings, like these are the different like if you want to do the post processing, so different post processing utilities are given here. Okay, and if you go here in the data conversion, so like we generally use that foam fluent mesh to convert the fluent meshing into the foam data. So like if you have a like a GMV kind of data, then you can use this utility. This is the for the text plot data. So if you want to convert foam data into the text plot for the post processing, then you can use this foam to text plot 360. Okay, so this is if you want to convert the foam data into the VTK file, because ParaView sometimes only understand the VTK, so then you can convert foam data into the VTK file. Okay, so this is for the post processing. Similarly, if you go to the pre-processing, pre-processing, so there maybe there will be this kind of utility, like if you can convert into the different mesh data. Okay. This is not given here. Maybe that maybe in the no, see here the different codings is given here. So if you want to convert one data into the another form, so suppose you have exported some mesh from the Fluent, then you can just type this command Fluent 3D mesh to foam, and then you can convert this data into the foam data. Okay, similarly sometimes you use Gambit to means to perform your meshing. So if you get that dot Gambit file, and then you can use this command, that is the Gambit to foam, then you can convert that into the foam meshing. Okay, so GMS data you can convert. So this is the this different option that you are seeing here for the pre-processing. So if you want to convert mesh data into the foam data, then these are the different things that you can see. So you don't need to touch anything. Okay, so this is just coding is given here. This is like a terminal command. Okay, these are the different things are the terminal commands that you have to type on the terminal, and then it can convert the data into the respective. Okay, so it depends upon that which software you use for the meshing. So sometimes it happens that you have means you cannot generate the complex geometry using the OpenFOAM. Okay, in that scenario you can use different external software to create your meshing, and using that software you can use any of these commands to convert your meshing into the particular OpenFOAM polymesh folder. Okay, so this is utilities. So this utilities folder that you are seeing, there are different codings are given here. Okay, so we are not going to touch anything. Okay, we are not going to means change any default setting here. Okay, now if you go to the etc folder, okay, so this is just I told you that where every code is given here for the parallel processing, for the post processing, for the pre-processing. Okay, so we are not going to touch anything. But if you go to the etc folder, okay, so here if you go to the case dicts, then you can find that there is a cases examples is given here. Okay, so if you want to know that how this data you can use full, okay, so there are different examples given here. Suppose that you want to understand that how the snappy hex mesh, how much parameters are there, and how it can be useful for you. Okay, we are going to cover this snappy hex mesh in the separate class, because that is going to take means another one session on the snappy hex mesh only. Okay, but you can see that how this, if you go to the so foam 6 folder, and then if you go to the etc folder, and in the etc folder, if you go to the case dict folder, particularly to the case dict, then you can have different things written here. Okay, now suppose we go to the meshing, and in the meshing, if you go to the generation, then you can see here that different dict file is given here. Okay, and if you open this, like I open for the snappy hex mesh dict, so you can see that what are the different parameters are there, that you can have idea here. Okay, some of the idea you can see here, that how these are the one parameters, this snap is one parameters, this add layer is by one parameters. Now if you have some geometry, how can you use that geometry in your snappy hex dict file? Okay, these are the parameters that is a source. So generally this snappy hex has three parameters is important, that is the castellated mid, snapping and add layers. Now this castellation has the different parameters. So these are the dictionary for the castellation. Okay, similarly there is a dictionary for the snap control, and similarly there is a dictionary for the add controls. Okay, this is for that if you want to write your what folders you want to write up, that is for that purpose. Okay, so you can see that this case inside the etc, this case dict is the important for to understanding that what is are the different utilities are available in the OpenFOAM. Okay, so using this folder, you can have some idea about the different processes. That is why I told you that there is a number of parameters that we are not able to cover even in this 40 hours. If you open this annotated, then you can see here that there is a number of parameters. Okay, so you can see that how many these are the different parameters are there. Some of you have aware about this. So like there is a create baffled dicts, create patch dicts. Okay, similarly this decompose paradict for used for the parallel processes. Okay, foam hex mesh dict. Okay, foam data went to dict. Okay, so these are the different parameters that you can see. Okay, now suppose you want to use some of these parameters in your test case. Okay, so it is always better, means generally what I do, I open this OpenFOAM 6 folder. Okay, and I can go to the tutorial folder. Okay, I can go to the tutorial folder. Okay, now suppose you want to understand some of these parameters, so we can use that find command. Okay, suppose you want to understand that, suppose first we can understand from here. So this create patch dict, so there is a different things are written here. So what is this means parameters is related to each other, that you can means understand from here. Okay, and if you want to, even if you are not means clear that why this parameter is means useful for your case and how you can use these parameters, then you can find test cases here. So I can use this find command if you are aware about this. Huh? Okay, sorry. Okay, so you can see here that for this particularly this function object, that is the create patch dict, you can have number of examples. Okay, now whether you want to simulate the multi-phase flow, or whether you want to simulate the incompressible flow, or whether you want to use for the combustion flow, based on that purpose you can means look at this example. Okay, so maybe I can take one examples from here. So let's take this incompressible one. Okay, so we are going to this week 6 day 1. So in this folder we are going to copy this folder, that is the incompressible pimple foam laminar, and here you can find this create patch field. Okay, then you can use the cp-r. Okay, first let me create the OpenFOAM 6 environment. Okay, see, please also you also try to do whatever things I am doing on my terminal. So cp minus r, then we can go to the foam tutorials. And from your foam tutorials, we are going to have the incompressible and this folder that I want to copy. Okay, this I can copy here and I can paste here. Okay, now I want to copy this folder at the present location. So that is why I need to put this dot. Okay, now I can see that there is this folder. Now we can go to the this this folder that we are going to work. So if I open here, so this is the test case that we are currently working on. Okay, so now if you see this all run, so here you can see here that it is going to first run this block mesh, and this then it is going to run this create patch. Okay, so we have idea that this whatever this create patch is going to do, it is going to do on the background mesh. Okay, so this block mesh is going to create a background mesh, and on that background mesh this create patch is going to perform this operation. Okay, now if you open this create patch folder, okay, so you can find some instruction here. So you can see here that it is written that from a given boundary faces, it is going to create a new patch. Okay, so till now you have idea that what is the patches. Okay, so patches is that whether we apply the boundary conditions. Okay, so if you means if you have studied our class on the block mesh dict, then you can have idea that these are the patches. So where generally we apply the boundary conditions, this is are called the patches. So using this boundary faces, okay, we are going to create a new patch. Okay, that boundary faces can be either a set of patches or the face set. Okay, so using this face sets and these different sets of the patches, we can create a new boundary faces or new patches. Okay, and there are different type of boundary conditions that you can create. So like you can create the cyclic boundary kind of the conditions, and this is the incorrect cyclic type of boundary condition we can create. Okay, okay, so suppose this is the examples that is given. It is creating one new patch, that is the cyclic half zero. Okay, so if you go to the if you open this current uh, this sorry, let me first run the block district. So now we have this polymesh. So if you open this, so you can have generally there is a moving block, moving wall, bottom wall, left, right, and front and back. Okay, so currently there is no any patch named as the cyclic half zero. Okay, now we are going to create one means this whatever the patch we are going to create that have this kind of the information. So the type would be cyclic. Okay, and the another cyclic patch will be cyclic half one. Okay, so if you remember that I told you about the cyclic patches, that cyclic like patches has the two different patches. It shares information between the two patches. Okay, so here this one patch is the cyclic half zero and another patch is the cyclic half one. Okay, so these two patches are connected to each other. Okay, so I think you have means you are understanding what I want to say, that so this is the one patch that we are creating and this is the another patch. Okay, and these two patches are means connected with each other with the cyclic information. That patch, that boundary condition we have already see in the FB patch field class. Okay, so this is how we can use the means construct this different patches, and from where it is constructing this is taking a f set of the face set, that is the f0. Okay, now if you open, okay, so this set should be defined somewhere. So this is creating from the set F0. Let me open the ParaFOAM first. Okay, so it is showing that there is a missing boundary condition for the left patch. Okay, so currently we are just opening the folder by I type 0.org. So this ParaView is not going to read this 0 folder. Okay, so now we can open this in the ParaFOAM. Okay, if you might face this issue in the ParaFOAM, so like it is, if it is written that cannot find the patch entry for the left or any other boundary condition, it means that this there is a missing in the, there is something missing in the this folder, that is the 0 folder. So you can just type 0.org, and after that you can to run this case. Okay, so I can see that this is the missing that we have created. Okay, okay, so if I go here, so here there is a wall, empty, left wall, bottom wall, right wall. Okay, so this create patch, it is creating from the F node. Let me just run this create patch command. So let me run this command, create patch overwrite. Okay, so if you run this command, it is saying that it is creating polymesh for time is equal to 0. So since we have a this 0 folder, so you can see here that if you open this boundary, so it has created this these two patches. Okay, so for time equal to 0, it is running the creative patch, and it has created two new patches, that is the cyclic half 0 and cyclic half 1. Okay, and it is saying that moving face from left to patch 5 and right to patch 6. Okay, okay, so I try to understand that how it is capture this left and from left to patch 5 and right to patch 6. Okay, so I will get back to this into next class. Okay, so actually I want to try to understand. So everything is okay for me, but how? Okay, sorry, my so see here it is giving the source. So here you can see here that this is constructed from the patch left and this is constructed from the patch right. Okay, so means either if you are giving the source, so this is the source that should be defined here. So I was confused in that purpose. Okay, so this is not defined here because it is already constructing from the patches left. Okay, sometime it what happens that we define the set of the faces source into the topo subject in the system folder. Okay, so either you can construct from the set of the source, or you can define the patch here. Okay, so that is why this if condition is given here. So I was confused in this. I did not see this line, so I directly go to this line. Okay, so either you can construct from the set of the sources, that is the face set, or you can construct from the patches. Okay, so if you are constructing from the patches, so you can see here that it is constructing from the left patch, and similarly it is constructing from the right patch. Okay, so there, if you, even if you means this, if you have a number of means if you are using the topo set dict kind of the utility, then you don't need to write this line. Okay, you can just select a number of face set, and using that face set you can construct a new boundary patches. Okay, I hope you are clear with this. Okay, so this is one way of creating the means like this create patch dict is important for you, so you can create a different kind of the boundary condition using the this create patch dict kind of things. Okay, similarly if you go to the this topo set dict. Okay, so let me see that what I wanted to show you. Okay, so here you can select a different kind of the information from the given mesh. So you know that in a mesh there is a, like you have a cell center, you have a face set, you have a cell set. So in this, using this topo set dict utility, you can select a number of cells or a number of faces or number of a boundary patches. Okay, and you can perform a different actions. Like these are the actions that you can perform. If you want to clear out a different set or a different zone, then you can use the clear command. You can invert, you can use the invert command. You can remove the different sets or zone. Okay, you can add new cell set. You can like means if you have already cell set, then if you want to add some set into that given set, then you can use this add command. Similarly, if you want to delete some source, then you can use this delete command. So these are the actions that you can perform using the topo set dict. Okay, and if you want to these are the operations that you are going to perform for the cell set. Okay, so these are the number of operations that you are going to perform for the cell set. Okay, so these are the different operations that you can perform on the cell. So means only you are particularly working on the cell things, these things you can perform. Similarly, there is operations related to the face set. So if you want to delete face set, or if you want to add some face set, then these are the number of the uh, means operations that you can do on the face set. Similarly, there is a operations related to the point set. Okay, so let me give you one example. That is the means very means I think that will clear every concept of this topo set dict if we are going to see this example. So I am taking one examples from the multi-region solver. So we can go to tutorials, and here in the heat transfer, there is a CST multi-region solver. Okay, so if you go to this multi-region, there might be a topo set dict. Okay, so this is a topo set dict that we are going to use. So if I am going to see this example, this is means I think most of the important utility from the topo set dict is given here. Okay, so means this is example that I am going to use. If you want to know other utilities of this topo set dict, then you can refer to this that is what I am saying, that this go to the this case dict folder, and in this case dict you have given information related to the other utilities. Okay, so let me copy this folder, this multi-region solver test case, and let me copy into the this folder. Okay, so here if you go to the this topo set dict, so see, this is the different actions that we are going to. So first you have to create a means first you have to create a one means a sub dictionary with the name of the actions, and in that dictionary we are going to perform this number of the operations. Okay, so first let me create the this background mesh. So let me close these things. I can type OF6 and then I can show you this block mesh. See if I show you this block mesh. Okay, so this is the block mesh. Okay, so currently there is no any different zone. So if you go to the this mesh part, then you can see that there is just max x, max y, min x, min y, min z, max z. Okay, so there is no any zone like heater, or if you have a fluid flowing through it. So there is not any this till now there is no any multi zone. Okay, we have a just a simple block. Okay, having some number of cells. So this is currently at this level. Now we are going to use the toposet dict. Okay, so if you see this toposet dict, so first it is starting from this lines. Okay, it is saying to create a new number of the cell set. We are selecting the new cell sets within this given box. Okay, so this is the source that we are giving here. So that we are selecting a box with this mean coordinate, and this is the max coordinates. Okay, so the means whatever the cells lie within this mean value and this max value, whatever the n number of the cells are given with this bounding box, all the cells are going to selected, and it is going to name as the heater cell set. Okay, I think you have this idea. So let me just first comment out all these things, so then you are going to understand better. So if you go to here in the constant folder, so there is no literally there is no any polymesh folder. Okay, and there is means there is no any mesh information in the given this different folder. Okay, so currently no, sorry, there is a polish mesh, but currently there is no any information related to this different multi regions. Okay, so let me just run this toposet dict. If I run this toposet, okay, so it is saying that, so currently we have just turned off everything, just we have these lines. Okay, so it is saying that, so it is saying that created cell set with the name of the heater cell set. They see we have given the name the heater cell set. Okay, and what from where we are selecting the cells, we are selecting the cells within this given box. So you can see that it's writing here adding cells with the center within the boxes with this minimum coordinates, and this is the maximum coordinates. This is the min x, this is the max x, this is the min y, this is the max y, this is the min z, this is the max z. So whatever the number of cells are lying within this given bounding box, all the cells are going to be added with the name of the cell set, that is the heater cell set. And how many cell set you can find? There is a size equal to 40. So within this given bounding box, there would be 40 cells that is selected using the toposet dict. So if I open this ParaView now, ParaFoam, why this screen is blank? आ रहा है ना स्क्रीन पे? Okay, sorry. So if I show you this ParaFoam, okay, so there is one box, and if I include the sets, then now here you can see here that apart from this different mesh parts, you can now see here that there is a heater cell set. If I all the turn off, and only turn on these things, that is heater cell set. Okay, so you can see here that this is going to be heater cell set. Okay, so this number of cell set is selected from the given background mesh, and it is known as the heater cell set. Okay, so these are the number of cells, that is around the 40 cells. Okay, so this is the 1 2 3 4 4 into 10. If you multiply, this would be around the 40 cells. So this number of the cells is selected using the this toposet sub dictionary. Okay, similarly, now I think now I can explain everything. So what is the actions that you are performing? Okay, so this is the new number of cells we have selected. Now you can easily understand that what is this line. So it is saying that we are not creating new cell set. We are adding some cells within this cell set of this bounding box. Okay, so it means that we have already cell set defined as the heater cell set. Now we are selecting few new cells and we are adding to this name, that is the heater cell set. Okay, so better this again. I can run. So you can now again they see. So earlier we have selected 40 cell set within this cell set. Okay. Again we are selecting the 80 cell set within this bounding box. Now if I go to the ParaFoam, if I show the sets, okay, so you can see here that earlier there was only we have this heater cell set. Now we have added it to this. Okay, this is what add command. So earlier we have selected only uh, few new cells, and now we have added some new cells. Okay, so that is how it is going to work using the toposedics. Okay, now whatever the cell set we have created, okay, this was earlier, this is only cells. Now we have created one cell zone set. Okay, so means it is creating one zone. Okay, that is defined as the heater. Okay, so that is going to define as a heater. So we are creating this different number of the cells that we have created from using these two sources. Now we are defining this as we are converting into the one zone where we can apply our own boundary condition. Since it is a multi-region solver, so we have a different region. So that is why we are creating one different zone with the name of the heater. So using this set to cell zone command. Okay. So this is how this is going to work. Similarly, we have created this left solid. So now it is clear to you. So that we are not means I think I don't need to explain for the left. So similarly, we have created left to solid, and we have created one zone with the name of the cell left solid. Similarly, we have created the right solid, and we have given the name equal to the right solid. Similarly, we have created one top air cell zone. Similarly, we have a bottom air cell zone. Okay. So I think similarly you can find different examples for the this different examples that you are given here. What is the new command? This is the add command. If you want to delete some cells from a given boundary mesh, then you can use this delete command. Okay. So if you want to add some more means subset to the given cells, then you can use this subset command. Okay. So this is the different action that you can perform on a given background mesh. Okay, so these are the examples that is given here. Okay, how you can convert cell into, suppose sometime it happens you have already given zone. If you want to convert that zone into the cells, then you can use this zone to cell command. If you have a face number of face given, and if you want to convert this face zone to the cell, then you can use this face zone to cell command. Okay, so there are different parameters that are given here, and you can go through it. Okay, just like this, suppose if you want to select some cells within a given cylinder, then you can call this cylinder to cell command. Okay, and this is the radius of this given cylinder. Sorry, this is the height of this given cylinder, and this is the radius. Okay, so that is how you can create select a number of cells from a given cylinder. Okay, similarly you can we can select a number of cells within a given sphere. कौन है भाई? Okay. So similarly, we have means this different utility that you can use. If you have a, if you have a given a, sometime it happens that you are given a surface, like if you have STL file, if you want to convert that all the cells within this surface to be selected, then you can use this surface to cell command. Okay, maybe I can show you one example of this surface to cell command. Okay, this similarly you can have this filled to cell command. Okay, similarly you can call this so this is useful that if you want that only select those, suppose we have given a field that is u, and you want to select only those cells who has the velocity greater than this 0.1 and less than just 0.5. So all the cells having this mean and max value, between this mean and max value is going to be selected if you are using this fill to cell command. Okay. So I think means I don't need to means go through it. You can just by going through this folder, you can understand everything. Okay. And where you can find this folder, just you need to go to this annotated, and you can have this better idea about this different folders. Okay. So this decomposed predict that is for the means parallel simulation. So if you open this, so you can see here that this is things that you are going to work on the. So let me copy one test case for this parallel simulation because it is important topic. Okay. So I have taken this motor test case from the OpenFOAM motorbike. You can just type. You can just search here in the tutorials. That is the motorbike. Okay, and you can copy this motorbike case. Okay. So this is a test case that we are going to run into the parallel. So if you open this, so let me first show this by default. So this is the uh, files that you can get from this annotated. So if you to understand this decomposed predict, you can open any from here. You can have better idea. This everything is written here. Okay. So suppose you have a suppose means you are working on a system where there is a n number of cores. Okay, so in that way you want to simulate your simulation into the in multiple processor. Okay, so that you can specify n. So suppose you have a n equal to, you have 4 processor, so you want to run your simulation into the 4 processor, so that you can define here. So like here if it is written 2, it means that you want to simulate your simulation to the 2 processor. Okay, so this is these things that you can specify here. There are some constant that you can if you want you can give, but generally means whatever the cases I have worked, I would not even use this option any times. Okay, because means if you want you can use. So what is the constant? So constant that if whether you want to preserve some things or not. Okay, so suppose like this is the like preserve waffles. Okay, so in that scenario it is saying that owner and neighbor of a given a waffle should be on the same processor. So if it is going to the decompose the your meshing into the n processor, then it is going to follow this constant. Okay, so it is not going to change the keep and neighbor of a given baffle. Okay, similarly if you want to preserve the phase zones, so if you have two means two different phase zones, so if you want to preserve the phase zone that it should be lie on the same processor, then it is going to constant this condition that you are applying here. Similarly, if you have a patches, then if you want to preserve the patches, then it is not going to destroy this constant. Okay, so like in the scenario of the like that we have worked on the cyclic boundary condition, cyclic EMI kind of condition. So you want that whatever the cyclic boundary condition we are applying between the neighbor and owner. So in that scenario, these two patches that where we are applying this boundary condition, it should be lying on the same processor. It should not go on the different processor. So it is going to preserve this constant that we are applying here. But in my cases, wherever I work, I have never used this constant condition. But if you want, you can utilize one of these constant based on your requirements. Okay. So here it is means how it is given here, that how you can write this different codes. Okay, like if you want to preserve the phase zones, so you need to write the different zones here. So like here I want to preserve this these three zones, that is the heater, solid 1 and solid 3. Similarly, if I want to preserve the cyclic patches, then I need to specify the patches here, like cyclic half 0, cyclic half 1. Okay. So these things, if you want, you can do, but means till now I have not used any of these things. Now this is important, that what are the different methods do you want to use. Okay, so generally there is a like 6 type of methods. Okay, but most of the times I have used these 3 methods, that is the method Scotch, hierarchical and simple method. Okay, so what is the this different 3 methods is for decomposition purpose. So I will explain. Okay, and this is the important if you are doing the 2D decomposition of the structured mesh. So if you have a only structured mesh and given into the 2D, then you can use this structured kind of the method. Okay, so this method, that is the that method that you are giving here. So this method is used to decompose your domain. Okay, so like you want to decompose this your given mesh into the 2 subdomain, means you want to simulate into the two parallel processor. Then how this decomposition is going to work, that method should be defined here. Okay, so whether you want to use the Scotch, hierarchical or simple. So let me show you the example. So for examples, this motorbike case, you want to have simulate into the 3 processor. Okay, so that is why we are decomposing into the 3 different different meshes. Okay, so whatever the this motorbike case is given here, it is going to decompose into the 3 different mesh zones. Okay, and it is going to solve the boundary means governing equation on the 3 different parallel processing. Okay, now how these things, this subdomains should be decomposed, that is something is depend upon the method that you are specifying. Okay, so it can be hierarchical, it can be Scotch, or it can be simple. Okay, so generally these 3 methods uh, you are going to use if you are going to work on the parallel processes, that is hierarchical, simple and Scotch. Okay, so what is the simple? Simple is so simple is going to you are going to specify some coefficient. Okay, so simple is going to work like it is going to if you are going to specify like 411, so it is going to specify that the number of cells lying on the x cells should be decomposed into the different uh, 4 different zones. Okay, and second is for the y. Okay, so it is going to decompose the y number of the cells lie within the y direction. It is going to be only, it is going to have only one decomposition. There is not going to be decomposition on the more than one. Similarly, there is only going to be z. Okay, so this is required when you have a this large number of cells only in the x direction. Okay, so then you are going to decompose your given mesh into the 3 into 1 into 1. Okay, now here this direction is fixed, that is the x y z, this order is fixed, x y z is order is fixed. But if you want that this order should be not fixed. Okay, for example, here in hierarchical you can change this order. This you can give here like z, x and y. So this is something different between this simple and the hierarchical. Okay, everything is same. So this here you can you can give order from your side, but here the order is fixed. Okay, now what is the Scotch? There is no requirements of order. Okay, so in a Scotch it is means from the simulation side, it is going to select the order means by optimizing the number of cells into the given processor. So if you are a 3 processor and you are using the Scotch method, then it is automatically going to select 3 going to divide your domain into the 3 subdomain based on the optimized solution. Okay, so generally means in my scenario when I worked on the complex geometry, so generally I use the Scotch. Okay, because in that scenario I don't need to understand that what is the number of cells lying in the x direction, y direction, or z direction. In that case, if you are using the Scotch, it is automatically going to uh, take the optimum number of cells into the divided subdomains. Okay, so these are the three methods that is important to understand for you at this level. Okay, now if you want to run this simulation, this motorbike, so so is so first you need to create the background mesh. Okay, so let me first so first let me create the background mesh. So see snappy hex mesh, whatever the utility that you are going to work means given in this folder, that is annotated folder, that is a kind of the pre-processing tool. So you are going to work on the background mesh. You need to have a background mesh. Okay, so that is why I need to create the background mesh. Okay, now once you run the background mesh, we need to run the snappy hex mesh. Okay. Okay, so there is no currently this motor try surface folder. So we need to run this command. So I will explain this. Uh, I will explain this snappy XMS. Then you can understand that what is this surface extract feature, and means why this try surface is required. That we are going to understand. So currently, this run this. Okay. So let this snappyx run in the background, and then we are going to understand this how you can run the this means run parallel simulation. So generally, you just if you are going to type this decompose per, this is the command for running in the parallel. So if you are going to type this decompose per, so it is going to uh, means using this subdomain. So how many domains you want to decompose, that is going to work here. So it is going to decompose into the means if you are specifying 3, then it is going to decompose into the 3 different subdomains. Okay. So based on these things, it is going to decompose it. And if you are decomposing into the 3 subdomain, then you are going to specify the n means number of the processor. Okay, suppose if you are decomposing in the 4, then you are going to specify here the 4, and this is the command that you are going to run. Okay, so this is the MPI run, and this is the number of processor, that is the NP is short for the number of processor, and here you are specifying that how many number of sub processor you want to solve governing equations, and this is the solver that you want to solve. Here it can be means simple form, pimple form, interform, whatever the solver that you want to use, that you can specify here. Okay, now here you are, since you are solving the parallel, that is why you are writing as a parallel simulation, and whatever the output is going to given here, that you are going to save into the this text file. Okay, so this is the how you can run this parallel simulation. So first let me uh, finish this simple snappy XMS, then we are going to run this command. Okay, so these are the different things that you can see here. Now the next important thing is the set field dict. Okay, so let me again. So again we can say we can open this set field dict. Okay, and we can see that how this syntax is going to work. Okay, but we can again copy one test case from the tutorial folder. So if I find iname, okay, so we can see there is a number of test cases available related to the set field dict. Okay, so based on your requirements, you can take one cases. Okay, maybe with this time we can take some cases from the multi-phase solver. Okay, bubble column, multi-phase. I want to take a case of the bubble flow. So maybe I can take this case. Okay, so this we can take here. CP minus R. Let's create the background. We have 6. CP minus R. Home tutorial, and here we can paste. Okay, now I want to copy this case here, present location. Okay, so now I can go to the bubble column. So if I open this bubble column, you can see here that there is a set field dict. Okay, so again this is a pre-processing tool, so we need to have a background mesh. So we will create a mesh where there will be a number of cells. Okay, and in that number of cells there is a first initial boundary condition. So you can see here that there is a already different boundary condition are given here. Okay, so out of those boundary condition it is going to work on the alpha dot here. Okay, so here there is a there is going to be one alpha dot here. Okay, so that is where we are going to work, that is the alpha dot here. Okay, so present at the initial condition, if you see, so there is a already given boundary condition. So there is a inlet boundary condition, there is a outlet boundary condition, and there is a walls boundary condition. Okay, but this boundary condition are given only on the given patches. Okay, so inlet, outlet, and walls, on these patches this boundary condition is going to apply. But out of this boundary condition we want to select some number of the cells from the background mesh, and on those number of cells we want to specify this value equal to the 0. Okay, so let me first create the background mesh. So first we need to create the block mesh. Okay, and if I run block mesh, after block mesh if I run ParaFoam, so this is something, this is how the background mesh, and this is the boundary condition. Okay, so if you open this boundary condition, so you can see here that inlet, it is the value equal to given equal to the 0.5. Okay, so you can see here that at the inlet the value is around 0.5. Okay, so this is the inlet, the value is around 0.5. Okay, similarly if you see at the outlet, the value is given equal to the 1. Okay, so here at the outlet you can see here that value is around 1. Okay, so you can also turn on the patches. You can see the name of the patches here. Here if you type, it will going to show you the number of patches, no name of the patches. You can see that the inlet the value is around 0.5. So from this label you can see here that value of this inlet is around 0.5, and similarly at the outlet you can see that value is around 1. Okay, but currently there is no any value given inside the any cell. Okay, so it is this information that we are going to if after typing the cell set, what it is going to see, it is saying that by default all the cells has going to have value equal to the 1. Okay, so currently you can see here that all the cells has value around 0. So these are the different cells. So all the different cells, the value is going to equal to around 1 if I means after typing this cell set. Okay, so this is going to be default value, but it is again saying that the number of cells lying within this box should have the value equal to 0. Okay, so apart from this box to cell, all the value equal to 1, but within this box the value is going to equal to the 0. So this is what going to do this this cell set is going to do. Okay, so let me first type this cell set command, and then you are going to see a set field. Okay, so you can see here that the internal value equal to the alpha dot here, and within the cells this is going to set some values. Okay, now if I type paraFoam, and if I going to select the alpha dot here, so you can see here that this box that we have selected has the value equal to 0, and this box is value equal to the 1. Okay, so earlier So first of all, there is a value equal to 1, but within this given box. Okay, so if you select, if you see the means if you see the values of the data axis, okay, so you can see here that from means from the value equal to 0 to 0.5 and y value equal to 0 to 0.71701, this is going to value equal to the 0. Okay, so you can see here that for y equal to the 0 to the 0.701, so this value is equal to going to the 0.701 something here. Okay, so up to this value, the value equal to the 0, so this is going to equal to the 0. Okay, and rest is value equal to the 1. Okay, so this is how you can adopt this set means sorry, set fildic to modify the value within the given cells. Okay, so this is just one option. Here you can use n number of the option here. Okay, so if you want to show me that how you can even say, select the cells within a given cylinder. Okay, so let me show you. So if I type this set field, so you can use this test a banana technique to check that what are the different options is available here. So you can see here that there are different options. You can select the cells within the given box. You can select the faces within the given box. You can select the cells cell to cell within a given cell number of the cells. Okay, so you can there particularly specify the number of the cells, and from that option you can just select the cell to cells. Okay, so like you can select use this cylinder to cell option. Okay, similarly there is means like sphere to cell option. Okay, so these are the different options that you can adopt. And how to know that how means how you can adopt this utility. For that purpose I have show you this toposet dict. Okay, so this is the similar concept that is adopted from the toposet into the set field dicts. Okay, so similarly like here we use for the box to cell, this is the source info. That is the similarly you can see here, you are seeing here same type of approaches are adopted here for the toposet dict. Okay, so like source info box, that is the min points and that is the max points. Similarly, if you want to know that how this sphere to cell can be used, so similarly approach you can adopt here. That is a sphere to cells, and that is you are going to give a one cell center, and from a given radius, it is going to select all the cells within the given this sphere. Okay. So this way you can select the cells within the given cylinder. So for that given cylinder, you need to have a one center point at the top, at center point at the bottom, and from this center point top and bottom you are going to give a radius. So within this given cylinders, it is going to select all the cells. So this is how you can adopt this toposet dictionary for your set field dict. Okay, so that is how you can use this set. Maybe I have one bubble case that I can show you. So I can show you these two examples. Okay, so this rising bubble case. So let me first create the background mesh OF6 block mesh. Okay, so in this example, I am going to show you that how this cylinder to cells utility you can adopt. This is the background mesh that you can see, and if you see alpha phase, okay, it already has been adopted. So this code has been already adopted. So what we are you are seeing here, so there is a one cylinder to cell option. Okay, now we are giving one point at the top and one point at the bottom, and within this given radius all the cells are going to be selected, and within that within this cylinder all the value equal to going to be 0. Okay, so if you see, so everywhere the value is 1, So everywhere at the given cells, the value is around equal to the 1. But within this cylinder, so that is one kind of cylinder that you can see. Within this cylinder, the value is going to equal to the 0. Okay, so this is how you can select the number of cells within the given cylinder. Okay, if you have some 3D condition and there you want to select the cells within the given sphere, then you can use this kind of the utility. Okay, so this is one kind of, let me run this simulation because I'm going to show you this ParaView automatization using that simulation result. So let first run the test case, and after that we are going to see the result using the ParaView, and also I am going to show you that how you can use the 1 minute. So let me run this case only, and we are going to work on that only. Okay, so let it be run in the parallel background. Now I think this snappy hex mesh can will be finished till now. Okay, so this is the simulation of the result of the snappy hex mesh. Okay, if I run this ParaFoam, okay, okay, so this is the motorbike case. Okay, so we are going to run a simulation over this motorbike. So this motorbike is the means STL file that is created from the some CAD modeler, and from that it is exported in the OpenFOAM, and using this snappy hex mesh we have created the mesh around this object. Okay, that is the motorbike. Okay, now we are going to run simulation using the decompose. Okay, so if we use this decompose command, okay, so if we use this decompose command on this motorbike case. Okay, so if we use this decompose command, then it is going to use this follow this decompose file. Okay, and from this decompose file it is going to use this scotch method. You can use any type of the method that you can say hierarchical method or simple method, but the advantage of using the scotch that it is automatically going to the divide the number of cells based on the optimized value. Okay, so we can run here decompose. Okay, so you can see here that it has transferred the number of cells into the three processors, that is the 0, 1 and 2. Since C++ works from the 0, so that is why the first processor is named as the 0, then second one is the name as the 1, and third one is the name as the 2. Okay, now you can see here that the processor 0 has the this number of cells, and processor 2 has a this number of cells, and processor 3 has a this number of cells. Okay, and this is information giving that the number of faces shared with the processor is the around this 923 faces. Okay, and how many patches this processor is going to work, that is around equal to 2 patches it is going to work. And similarly here you can see that the number of faces is around equal to the 923. Okay, so this processor 0 sharing the number of faces with the processor 1 and 2, and these are the number of faces similarly for the processor 1 and similarly for the processor 2. Okay, so if you want to run the simulation, then we can use this readme first. So you can see here that the number of cells has been divided into the three processors, that is the processor 0, processor 1 and processor 2. Now if you want to run our simulation, so we can use this that is the MPI run, NP, and this solver. Okay. So let me check first that we copied from the simple form or some other. Yes, the case is related to simple form. So we can use this simple form solver. So remember that I told you that this command you have to start that you want to run your simulation in the parallel, and this is the number of processor. So how many domains you have decomposes your given background mesh, that you are going to specify here, and this is the solver name, and this is the parallel simulation, and that is the name of the file where you want to store your dictionary, sorry, whatever the simulation you are printing on the screen that you want to store into the text file, that you are going to specify here. Okay, so this is the MPI run, this is the number of processor, this is the solver name, that is the you want to run into the parallel, and that is the log simple form. Now if I run here, we are getting some error. Okay, so what is the error? So before running into this, let me run first the simple form. So it is saying that cannot file. Okay, so currently this 0.org we have hidden, so that is why it is showing the error. So we can rename it as a 0. Okay, so it is running. Now we need to again the decompose it. Okay, because if you go to the this processor, you can see that this 0 that we have earlier, it is showing that information. Okay, so we need to remove this all the processor, and we again need to decompose it. Okay, so for that purpose I can use this rf and pros this command. So that is going to remove all these three processors. Okay, so star means that whatever the files having the pre-name starting with the proc, that all file is going to be deleted. Okay, so if I enter this, then you can see here that all the processor file has been deleted. Okay, now again I can run this decompose per command, and again I can run this npi run. Again I am getting error. Okay, so that there are some syntax error in these functions. Okay, that is why that error was showing. So now you can see here that using this command, we are running the simulation, and we are printing this using this tail minus f command. We are printing the text file. Okay, so it is running. Suppose you want to see some result from the processor, different processor. So you can use this command. So suppose I want to see the result of the processor one. So during the simulation, I can go to the this ParaView case processor one command. Okay, and you can see here that these are the number of the cells that is shared with the processor one. Okay, and you can even visualize the u, that is the velocity. So these are the number of cells that is given to the processor one. So similarly, if you want to see for the processor 0, so then you can type this command, and you can see that these are the number of cells that is given to the processor 0. Okay, so you can visualize the u and p on this given processors. Okay, similarly you can see for the processor 2, 0 1 2. So this 2 is means the processor 3, so 0 means processor 1. So you can visualize the result for the different processor using this command. Okay, so these are the number of cells that is shared with the processor 2. Okay, and if you go through the files between the different processor, and if you see this u, you are going to find one value, that is the one boundary condition, that is the processor boundary condition. So it is saying that between 0 to 1, this is the type of the boundary condition that you are going to use. Between the 0 to 2, this is the boundary condition that is going to be used. Okay, so as soon as you are going to decompose your test case into the n number of the boundary patches, this boundary condition that is going to be by default you are going to see in these folders. Okay, you can see in the p also. So p also you can going to see that the boundary condition between the processor 0 to 1, this is the kind of boundary condition. Processor 0 to 2, this is the kind of boundary condition. Similarly, you are going to see for the different processor. So that boundary condition is applied to share the information between the two different processors. Okay, so from processor 0 to processor 1, this boundary condition is going to be applied to share the information between the different processor. Okay, so that is the different type of the pre-processing utilities in the OpenFOAM. Okay, there are n number of, like, you can, if you want to refine your mesh, you can see this dict folder. Okay, how can use this? So already information are given here. So for example, so using this topo set, you are going to select some number of the cells. Okay, for example, using topo set dict, we have the select the cells of the heater. Okay, as I shown you that we have selected the number of cells given from this box. So if you have defined this cell set, you can define here like C0. Okay, so from that cell set, that is the C0, it has selected one number of cells. Now you are going to perform this refined mesh on this cell set. Okay, on this selected cell set, you are going to refine the use this information. Okay, now there are different means refined method is available. Like if you want to do this global refine, then it is going to work on the global. If you want to only refine a given local patch, then you are going to use this method. Okay, Now there are different means if you are whatever the method that you are going to use, the coefficient should be like that. So if you are using this global method, you are going to use this kind of the approach. Okay, so what is the this in global, this tan1 and tan2 is there. So like there are three axes is given here. Okay, so that if you are specifying this tan1 equal to the this x direction, tan2 equal to the y direction, then tan3, that is the third direction, is automatically going to be the perpendicular to these two directions. Okay, so this is going to perform this means this refine operation perpendicular to this given direction, that is the tan1 and tan2. Okay, so this is the global global refine mesh utility that you are going to apply. If you want to refine only a given patch, then you can use this patch local information. Okay, similarly, if you want to use this means field based operation, then you can use this kind of coefficient here. Okay, so means if you type here in the form tutorial, you are going to see n number of test cases. So you need to play with those cases. CFD form tutorials. Okay, so you can see here that n number of cases are given for the refined district. Okay, so you can means you can just copy one test case and you can try to understand from here. Since you can see that a number of test cases are related to the just pre-processing tool. We have not still covered the post-processing tool. These are the utilities that is the related to the pre-processing. Okay. Now one means one important thing that I want to cover. Okay. So sometime as I told you that sometime you have a STL file and you want to convert that STL file into the, you want to select the number of cells within the given that STL file. Okay, so in that scenario, you can write this your cell predict like that. Okay, so by default we are having value equal to the 0. Okay, but if we have some STL file, so like I have this ellipse kind of the STL file. So within this STL file, whatever the number of cells lying within this given STL file, those value are going to be modified equal to 1. Okay, so let me close all these files. So means apart from means all this STL file value equal to going to equal to the 1. Okay, now let me run the test case, then you will have a better idea. So you can use this readme first file. So if I run OF6, then I'm going to create the block mesh. Okay, then after block mesh, we can uh, this we can remove this 0 folder. Okay, this 0 folder has been removed. Now we can copy this 0.org into the 0 folder. Okay, now I can run this. First let me show you the mesh. So this is the background mesh. What is the error? Okay, sorry. The problem is that we have already used the code stream. Okay, this topic I need to cover in more details. So let me first turn off this. This code stream I'm going to cover this code stream in another session, because it is going to take one session for the You can use this code stream for the creating the set field. You can select the number of cells within a given means topo set utility. For that purpose, you can also use the code stream. For the different boundary condition, you can use the code stream. For the different function utility, that for that purpose you can use the code stream. So this topic I am going to cover in a separate session. This complete code stream things. Okay. So that is why I'm turning off, and I'm taking this uniform field equal to the 0. Now I can use this paraform. So this is the background mesh, and if I show you alpha phase, so you can see that everywhere the value is equal to the 0. Now if I open the geometry, that is the STL file. So if I open this STL file, so all the cells lying within this given this ellipsoid. Okay, so there you can see that some of the cells is shared by this ellipsoid. So all the cells lying within this ellipsoid is going to be selected. So these are the cells which is lying between this ellipsoid. So these are the cells is going to be selected, and that value is going to be around 1. Okay, so you can see here that alpha dot phase is going to be modified with the value equal to the around 1. Okay, so we can now run this set field command. Okay, now if I open this paraform, so you can see there, this was the STL file. So if I go to the JOM, and I can show you that this is the this was the STL file that I have taken, and this STL file is created from using the CAD modeler software. And from this STL file, we have selected the n number of cells, and this value is modified equal to the 1. Okay, now if you want, you can run your simulation. Okay, so here the means the location of this file you can give here. Okay, so if you go to the this folder, so here you can see that there is a geo kind of a folder is here, and within this folder this STL file is given here. Okay, so that you can see here that we have given the location, and within that location we have this STL file. Okay, so this is how you can create how you can select the number of cells using this STL file. Okay, so we have simulated the result. So this is all about the pre-processing tool. So different pre-processing tool that you can see in the annotated folder. Still we have to go through this. I have already covered this parallel processing, and we need to cover this post-processing. Okay, so I think I cannot cover these things in today class. So I'm going to take one session on the code stream as well as this post-processing tools. Okay, but last topic that I want to cover, that how you can use this paraform for the automatization. Okay, so how you can use the code, how you can do the coding within the paraform, that we are going to cover now. Someone has question. So MPI run is the means you can say that is the terminal command. Okay, and in delta that you are seeing, so sometime it happens that you are decomposing, and what is I am not aware of that. What is the delta in decompose predict? Okay, Sudhin, that I will tell you in the next class. I don't know what is this delta. Oh, too many of questions are there. see, this I wanted to tell you, this all run that you want to know, uh, that is also a part of this pre-processing. Let me show you this. Mm, yes. So whatever the all run, all clean, and all mess that you see in your folders, the means the basics of that things is given in this if you go to the this case dict folder, and if you go to the in general, and there is a one folder that is known as the workflow. So within folder, if you go, you can see here that the what is the meaning of the different thing, and if you want to create your own all run, then you can just go through this, follow these instructions. Someone has already asked me this question in the earlier classes while we were covering first or second week. Someone asked that how this we can create all run and all mess and all clean. So this is where you can see that how what is the workflow, how we can create it. And if you go through here there, so this is the basic requirements. So this is information is given that you want to run this all run from the given folder. Okay, so the present working directory, you want to run this all run command. That is why this command should be given here. If you see any all run folder, this command is given here. Okay, and this is the source, that is the run function. So if you go to this tools home directory and bin and tools, then this run function, that this run application, run parallel, this all things are given at this run function. Okay, so let me show you that also. So if I go to the form OpenFOAM 6, and if I show you that run function within tools, and maybe somewhere it's given run function. So if you go to there, so you can see here that this all the run function, run applications is given here. Okay, run parallel is given here. Okay, compile application is given here. Transpose file is given here. So everything is given here. So that is why it need to the source here. So that why it is going to be source here. This dot command I already told you in many times. So dot means that it is going to source at the present terminal. Okay, and this where it should be sourced, so it will be sourced from here. Now it is running run application block mesh. So whatever the operation that you want to perform, block mesh you want to perform of your means whatever things, set fields, if you want to perform the set field dicts, so just you need to type here run application, and similarly you can type set fields. Okay, so this kind of approach you can apply to create your own all run. That was not a big task, as I told earlier also. Okay, so sometime it happens that you want to refine your mesh in multiple times. Okay, so in that case you can even use the this loop for 3 times. Okay, so it is starting from I equal to 0, and it is going to iterate up to the 3 times. Okay, and it is going to first run the topo set dict command, and then it is going to run the refine mesh dict. Then again this number of cells has been modified. Okay, so why this topo set dict is important to run again and again, because earlier if there is only 40 cells, if you refine the number of mesh, then now this 40 cells is going to be 40 into the 2, that is 80 cells. So now if you run the topo set dict, then it is going to select the 80 cells. Again you are going to refine the mesh, now this number of cells is going to be 160. So again if you are going to run this topo set dict, it is going to select the 160 cells. So that is why means if you are using this refine mesh dict n number of times, then you have to use this topo set dict n number of times. Okay, now if you want to run the parallel simulation, then you have to run this application, that is the decompose per. So this is the how you can use the this all run command. Similarly you can see for the in workflow, you can go through and you can see that how this is a simple task. These two things is important to write, and again you can means whatever the terminal operation that you want to perform, that you have to write run application and this number of the terminal. Okay, so you can just go through this folder and you can find this. Okay, now this is the how you can clean your cache. So you can prepare your own all run, all miss or all clean command. That was not a big task. Okay. So I think this line 1 to 3 line is clear to now. And no, this Jamshid, as I told you in the boundary condition class, that cyclic is a periodic is a type of the cyclic boundary condition. Okay, cyclic does not mean that periodic. Okay, periodic is a one type of the boundary condition of the cyclic type of boundary condition. Okay. Yeah, see, someone has asked me that whether this create patch field dict should be necessary in the system folder. Okay, that is not necessary. Okay, this folder, that is that whatever the folder that you are giving, so this topo set dict or this create patch, that is not going to be necessary into the system folder. Okay, but as soon as you are going to type this any type of command like set field dicts that you are going to type. Okay, so if you are typing just this command, then it is going to see that set fields dict folder into the system folder. If you are not in that folder, then you can find you can type this dict command. Okay, and if suppose you have this folder in the constant folder, so you are going to specify the dict name equal to this set field dict that is means you have to specify the location here, that I want to say that. Okay, so if you have that folder into the some another folder, then you need to specify the dict location of that folder, then it is going to work. If you are typing the even if you are typing the block mesh, and suppose that block mesh dict is not in the given specific folder. Okay, let me show. Yes, I can show here only. Suppose this block mesh is not given here, and this folder is present at the constant folder. Okay, so if you type block mesh here, then it is, if block mesh dict is not present in the system folder, here there is no any folder. Let me just delete this one. So if this block mesh dict is not present here, and if it is present in the constant folder, then simply you can specify the dict and the constant and the block mesh dict. Okay, so it is going to work. Okay, so by default you are typing this create patch dict or any other type, this kind of the pre-processing or the post-processing utilities, it should be present in the system folder. And if that dictionary is not present in the system folder, then you should need to specify the location. So just by typing this dict command. Okay, there are lots of difference between the topo set and create patch field. I think it should be clear to you by now. Create patch field, you are creating the different patches. Okay, and topo set dict, you are just selecting the numbers of cells. After selecting this number of cells, you can perform a different operations, like you can create a different cell zone set, or you can means like you can define some values on that. You can create your porous zone cell type kind of the zones that you want to specify. So this two has the different so then cell set means you want to just select that cell zone set is important if you are working with a different other type of boundary condition. For example, here I am working with the multi-region. So for multi-region, we have to create the different zones. Okay. So if you are seeing here in my screen, so you can see here that like we have this two different zones, that is the fluid domain and solid domain. Okay, so from the different cell sets we create the cell zones. Okay, cell zones means number of cell sets having the same type of the properties. Okay, so for example, you have created a cell zones equal to C0, C1, C2 and C3. Now you want to create all this cell set into the porous zone. Okay, where you want to apply the porous kind of solver. So you can specify this cell set, that is C0, C1 and C2, and this number of cell set can be converted to the single cell zone that is known as the porous zone. So that is the difference between the cell set and cell zone set. Okay. Okay, so this set to cell zone, sometimes it happens that you have already some cell set, and from this cell set you want to convert into the cell zone. See, there are real number of parameters in the topo set dict. Okay, so if I going to take one example of everything, then it is going to take a number of classes. Okay, so what happens, even if I today I'm going to tell you these examples related to these different parameters, you are going to forget. As long as you are not going to work for your means one physical problems for a given these parameters, you are not going to remember these things. Okay, so that is why I wanted to tell you that how you can get the information. You just get the information, you can search a test case into the tutorial cases, and from there you are going to work for your specific problem. Okay, so that is what I wanted to show you, and some of the important that is important things that already I told you. Okay, so what are the important utilities are there, and what are the important parameters from the topo set dict and cell set dict are important, that I have already told you. But if you are going to see all the parameters, it is not possible. Okay, so when you are going to work for your own specific problem, then you are going to of course you are going to struggle means half an hour or 1 hour, and you are going to figure it out, and once you are going to figure it out, you are not going to forget that thing. Okay, so this box to cell, set to cell zones, these different things are you are going to learn by practicing. Okay, on the different cases. Okay, so this delta things I will clear by tomorrow. Yes, yes, box to cell you have. So if you want selecting cells between the two box, that should be the minimum coordinates, and that should be maximum coordinates. So in the box, that should be like diagonal coordinates of the given box. Okay. So you are right, Sudhin, in this way, means you are means you got it correctly. Okay. Now the most important things that I want to cover before ending this class. So we have simulated this case. Okay, now we are going to work and we want to see that how you can use the ParaFoam Python package. Okay, so if I open this in the 6 and this ParaFoam, okay, so suppose you have started with this. Okay, now what I can see, I can go to the tools. Okay, and here there is option that is the start trace. Okay, so that I can click OK. Okay, and I perform everything. Suppose I have seen this alpha dot phase. Okay, and suppose I cut between the mid, and suppose I want to just see this direction. Okay, and this is how it works for the different iterations. And suppose after the iteration 100, I want to plot my result. Go to the alphabetical, plot over the lines, and maybe I can plot in the y direction. Okay, and out of this, I just want to take alpha alpha phase value. Okay, and then I want to save this data. Okay, so this is the number of operations that we perform. So what we need to do now, we just stop trace. Okay, so as soon as you stop the trace, you are going to get a Python code. Okay, so that Python code, so as I told you in the last class, we can open the terminal and we can create any kind of the file. So for example, I can create one Python file that is the extension with the .py. Okay, so maybe I can give this elliptical.py. Okay, so if I open, see, this is a Python. This is the code that I have created. Currently there is no any code. So what I am going to do, I just going to copy this all the codes and going to paste here. Okay, so these are different codes that I have. You can just whatever the operation that we perform at the given terminal, given ParaFOAM. Okay, so this all the performance has been written in the terms of the code here. Okay, so different performance that I will perform here, that has been written in terms of the code here. Okay, now if I going to load this code, it is going to automatically perform all the operations and it is going to save this alpha.phase. Suppose we have earlier saved this alpha.csv. Now we are going to save as a alpha1.csv. Okay, so we are going to save this alpha1.csv and we are going to perform all these operations. Okay, all this operation by using the code only. We are not going to do anything from our side. Okay, so let me again open this terminal. So again we are going to open this terminal and we have opened these things, that is the elliptical.ic.open. Now again I'm going to tools. Now we have to open the Python shell. So this is the Python shell that I open. Now I'm going to run a script. So after clicking the run script, I'm just going to open this elliptical.py. So if I open this elliptical.py, you can see here that it has automatically performed all the operations. Okay, and it has going to save one alpha.c. So presently it is running the script. You can see that it is running the script. And once it is finished the script, you can see that there is a one alpha.c1 CSV file. Okay, so whatever the operations that we have performed, that is going to performed by this script that we have written here, and we have written here by using the utility of the open ParaFOAM only. So we don't need to do anything, just we can start trace, and after you do the operations you can stop the trace and just copy that code into the this dot using this .py extension. Like there is a elliptical.py extension. Okay, and you can copy this extension code and you can use that code for means sometime it happens that you are doing the parametric studies, you want to save this kind of the file for the n number of files. Okay, so in that scenario this type of code is very helpful. Okay, so this in that way you can just load your Python code and it is going to perform the same operation. So you don't need to do these things one by one. Okay, means I think you got my point. Said means where this .py kind of the things can be useful for the post processing. Okay, so this is one approach, and there is another approach that you can use. So this is one approach, that is .py approach. Okay, so there is another approach that I want to cover. Suppose uh, where means which can any case we can take. I think we have simulated this one. So this motorbike case, let me means after running the simulation, if you want to see the results, means as a single domain, then you can use this reconstruct command. You can use this reconstruct command, so it is going to show you the results. Now we can delete this this three processor results. Okay, now if you want to again visualize this result, okay, so either you can start again using this Python start trace and then get the code, and after getting the code you can save that code as a .py, and again you can open the Python cells and you can do those operations using that .python code. Okay, otherwise you can also use these things that I want to show you. So maybe we can do this slicing in the z direction, and okay, we need to have slicing in y direction. uh, okay, so this is the result. Okay, suppose we have changed the background, so we want that background should be white, and suppose we also want to change the this result and we want to make this very beautiful. Suppose this is the result. Okay, okay, now what we can do, we can save the state. Okay, so if you go here you can use this from this file, you can use this save state. Okay, and you can give any name here. We can name this motor bike. Okay, so this present state has been saved already. Okay, so here you can see that motorbike.pvsm, this kind of state has been already saved here. Okay, now what happened, again suppose we want to get that kind of picture using means for the same type of the simulation. Suppose we are varying the inlet velocity for this bike. Okay, so we are performing a means parametric study, and we want to we want to save that that image that we are getting at the final simulation or the final test case final result. That kind of the task that we want to perform are the m number of the test cases. So for that purpose we can now uh, just open this test case using this ParaFOAM command. Okay, so now you can see that test case has been opened. Now we have to just load the state, that state that you have saved, that you can load here, and you can click the OK. Okay, so it is taking some time. Now you can see here that automatically it has created that state. Okay, so you don't need to go do all the task one by again. You have just loaded the state and it is automatically going to create you that 2D file that you are that we have performed the task earlier. So you don't need to again save this like you don't need to create this slice, and then you don't need to do this color change, and don't you need to do this means horizontal this things task that in you are performing a number of times, that you can save the state, and after saving the state, if you are loading that state, it is going to automatically perform this post processing. And now you can save this screenshot if you want for your result and discussion section. Okay, so this is just two example I've shown you how you can optimize your post processing result in the ParaFOAM. Okay, either you can create your own code or you can use load the state. Okay, so this kind of things you can perform here if you are doing the parametric study. Okay, so for example maybe I can show you one my paper. Experiment So if you see this paper, see this here also I have to do the same time. For example, I have done the this means this result I have created using one state. Okay. Now for other three cases, I have to just upload the this means that state that I have saved. Okay. So this state that I have saved, I have uploaded, and it has automatically created this kind of result. Similarly, if you see for this purpose, okay, so this is for the heat transfer. So I have created everything for the size ratio 1, and similarly it has created for all the ratio. So in my cases, I have done n number of parametric studies in all my papers. So for that purpose, this utility was useful. Okay, so for example, here I plotted the temperature. Okay, so I have to just do the this state save I have done for this one test case, and then it is done for the all the cases based on the. Okay, so this is for also the temperature. Okay, so this way you can optimize your parametric simulation for the post processing. Okay, so I think it is this class is useful for you for the post processing, for the function object, and for the utilities. We still need to cover this post processing of the OpenFOAM. It is not covered today. We have only covered the pre processing. So these things we need to cover. Maybe these things and the code string we are going to cover in the maybe in future classes, because tomorrow the thermophysical model is going to be covered, and some of the yes. Jamshid, what I mean to say that suppose you have a same test case, okay. Now you want to study the effect of the inlet velocity. Suppose you are modifying the outlet velocity. You are doing a parametric study. So for in that scenario, we are going to have a n number of this folder, such kind of, where only one parametric is changed. Okay, in that scenario, you are just need to upload this test case, and this result is going to, of course, it is going to vary. Okay, so in that scenario, this kind of the this save state kind of the utilities is important for you. I think you got the. And even you can just type in the Google. These things are related to the Linux or the your system. How many processor are there? That you can type in the any Google. Now there is a chat GPT. This kind of information you can get from there. So means how to check the number of processor that is related to the whether you are using the Windows or using the OS means Mac type of system. Okay, that you can find from the Google or Linux. Okay, so this is very important, and I think today's class is helpful uh, to optimize your post processing. So you can use the means different type of utilities. This is something I related to the ParaFOAM I just covered today, but in even in OpenFOAM there is a number of the post processing utilities. Okay, that we are going to cover in the next session, and we are also going to cover the code stream. So please, I'm going to upload these files, and please go through the everything and try to simulate from your side. And if you have any questions, just let me know. Okay, so thank you to all of you for joining this session. uh, Good night to all of you.